Hello everybody, this video is going to go over how to do calculations involving weak acids and bases. So I don't mean weak problems as in lame, I mean as in acids and bases that do not dissociate completely. And what that means is everybody's favorite thing is back. Ice tables, equilibrium, never goes away. So when we do these weak acid-base problems, we are right back to doing ice tables. So here's an example. One of the things I've noticed over the years is that when students are given a weak acid, weak base problem, they get stuck on the very first step because it is not common to be given the equation. You are expected to recognize if something is a weak acid or base, and then be able to write the dissociation for it. They will not always give you the equation. And so if you don't know your strong acids and bases, then you won't by default know when you see a weak acid or base. So here, why don't you take a second and try to write the dissociation of our acetic acid. All right, so there you go. We will use that equation to set up our ice table. So if you remember, it means initial, change, and the values at equilibrium. You'll often see me put a row at the bottom for the actual answer, but it's pretty traditional just to do these first three rows. So reading this question, we can see that when we start, we have a 0.5 molar solution of our acetic acid, and at the beginning, nothing has dissociated yet, so it's just 0. Now we look at the coefficients to see what the change would be. We're going to lose our reactants, and we're going to make our products. And because all our coefficients are 1s, we just have minus x, x, and x. Remember, if you aren't starting with 0 products, if you start with some products, then you would have to do a Q versus K calculation to determine which direction you're going. So that can be something that's a little tricky. But here you can see, obviously we're going to proceed to the right because we had no products at all, so we have to go that direction. Now our equilibrium row is going to be what we started with, minus x, and then here what we started with, plus x. So now you can set up your law of mass action using your equilibrium values. Remember, it's going to be K equals the concentration of your products over the concentration of your reactants. And the nice thing is 99.9% of the time you can assume that x is small, and so you can do that 5% rule. The idea here, if you remember your 5% rule, is that x compared to 0.5 is very, very tiny. But x compared to 0 of your products would be something that was meaningful. The analogy I've heard often is if you're a billionaire and you lost $100, you wouldn't really notice. But if you were really struggling and had, hardly any money and you lost $100, you would really, really notice, wouldn't you? That would be impactful. So x compared to 0.5 is negligible, so we can ignore it. And it simplifies our algebra. We do not have to use the quadratic. So now we can solve for h, and h is x, you can see here. So now that I know my concentration, now I can find my pH. One quick thing, sometimes they may not give you the K values. You may have to look at a chart to get that. Not something you would need to memorize. It's either given, or it's what you're solving for, or they just have you look it up. And now we do our simple pH calculation, realizing that our concentration is the same as X this time. And you can get your final pH. Now, be very careful that you do not forget things like coefficients and stuff, because the concentration of your hydrogen here may not have been a simple X. So a lot of people will solve for X and they forget to plug it back into the equilibrium row. So just be a little bit careful about that. Okay. Now the next part of this has to do with weak bases. I've noticed that we are much more comfortable with the acid equations because we're used to just plucking off one of those protons, right? But when you have weak bases interacting with water, people struggle with writing the equations. So here we have a weak base reacting with water. Water is going to function as the acid. It's going to donate one of the hydrogens, and we're left with this hydroxide. I really suggest paying close attention and practicing writing some of these base reactions out so that when you get one, you don't get stumped and forget what to do. Remember, they're interacting with the water. And this thing here is now our conjugate acid, isn't it? And this thing is basic. Remember also there's a difference between Ka and Kb. So be a little bit careful about that. Always make sure you're using the correct value. And you'll also notice here that we do not see water in our equilibrium expression, do we? Because what's the phase of that water? The phase is liquid. And we don't put liquids in our law of mass action, do we? So be careful about those kinds of things too. Look for the phases. So this chart is just trying to point out what some of the conjugate acids would look like once the base has accepted that extra proton. And once again, spend some time trying to see those patterns. I think that acid and base chapter is really hard for people because they don't pay enough attention to their conjugates, right? If you have an acid, what does the conjugate base look like? If you have a base, what does the conjugate acid look like? If you can get comfortable and familiar with those and those patterns that you see, then you're going to have a much easier time in this chapter getting your equations and your reactions. So here's kind of a generic way to write it. And you know what? No matter how weird and funky your base looks, no matter how complicated they are, you saw some of those strange bases on the previous slide. They have pretty funky formulas. They're kind of weird compounds. It really does come down to this, so don't make it more complicated. Count up those hydrogens, see where, how many each has, see which thing's the acid versus the base. It really does come down to this pattern recognition. I think sometimes seeing it in a generic form can be helpful because when you look at, go back to the previous slide, when you look at these crazy things, people panic and their brain shuts off, and we don't have that luxury, right? You can't panic. Think about the generics, and that can help you identify things. So why don't you take a minute and you try to write out the reaction here. We have ammonia dumped into water. Ammonia is going to be your weak base, which means it needs to interact with water to form a conjugate acid. And the poor little water is going to be losing one of those hydrogens. So let's see how you did. So here is my base. This is the conjugate acid. Water was functioning as an acid, and you can see here is the conjugate base. Now we need to do an ice table. Why don't you pause and try to plug in all your values? All right. Nice thing is we had 1-to-1 ratios again, so just simple x's to deal with. Now what's step 3? Can you remember? Now we set up our law of mass action. I'm super duper happy because I can use my 5% rule. I'm super lazy and don't want to do quadratic. I solve for x. The nice thing is this time, like before, it's a 1-to-1. Now, a lot of times people are like, whoa, it's the exact same numbers. It's the same thing. The pH is 4.52. No, it's not. No, it isn't. This was the pOH. This was not the concentration of H+. This was the concentration of hydroxide. So when you do your negative log of that, that's a pOH. I purposely picked the same numbers to be tricky because I want you to notice, and you've got to pay attention to whether you're solving for a pH or a pOH. One of those common things I like to trick people on. So be real careful. Now, this is something that people tend to forget, and you can get real stuck if you don't remember this, okay? Remember that water can self-ionize, right? We saw that in our previous lesson. And so if you are given the Ka of something, but you need to know the Kb, right? If you're dealing with a set of conjugates here, you can calculate it yourself using this fact. Now remember that this is temperature specific. If you change your temperature, you can't use the same numbers here. But the good thing is very, 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 very few problems would ever be at strange temperatures. And if they are at strange temperatures, they're going to give you enough information to act accordingly. Okay? So you can see here, if you know one, Ka or Kb, you can rearrange and solve for the missing one. That's going to be very helpful when we do our salts. Remember, when you put a salt into water, sometimes it'll be neutral, but sometimes it'll be acidic or basic. We'll have to use this fact sometimes when we do those salt problems. So make sure you really know it for these weak problems, but also for our salts later on. All right, everybody, I know that wasn't very long, but I hope it's a good refresher on the fact that we're right back to our old stuff, those ice tables you've done a bunch of before. All right, everybody, that was it. Hope that was helpful. Bye.